Well, hello everyone. I am Mr. Santos, and you are watching Introduction to OrCAD Schematic Capture for Students. Um, I am a teaching assistant for the University of Nebraska, where we teach a course called CEN 3320 Assembly Language Programming. And the purpose of that course is basically to engage students in writing firmware for a couple of microcontrollers, 8051, and then also the 8086 microprocessor. But as part of this course, they also have to engage in a PCB design project, and the purpose of this project is just to expose students to the entire PCB printed circuit board manufacturing process. What does it entail to have an idea in electronic form? Formulate a schematic, produce a PCB board, and have it fabricated. This entails a lot of information that has resulted in being a challenge for a lot of our students. So the purpose of the course is to alleviate some of these challenges, because they move on to a course CEN 4330, I believe, where they do a computer design project, which is very complicated. They have to write firmware for it. They have to design. Each individual student has to do his and her own design, and they have to do this, but they have to kind of figure out on their own, because of the course. There's so much information in the course and so much work. There's no time for them to learn about the PCB, so they have to learn it on their own, and this results in a sometimes frustrating experience for some of our students. So the 3320 was created to allow to offload some of this work and be prepared to take on these challenges when they move on to computer design. And then also they use that to in their final project, and having learned this material will greatly aid them in having a smooth experience when they're doing their final senior project design. So we have to do this. We're going to teach basically in this tutorial how to use OrCAD Capture CIS, and we're going to use version 16.6, which is the Lite version. And this is what you're looking at here. Basically, I have a finished project that we're going to show you how to do, to show the students how to do. We have a license to OrCAD in our classrooms, in some of our labs, that students have access to. But again, because of the steep learning curve that it takes to not only learn about PCB manufacturing in general, but also learning how to use this particular software, that is just very challenging. And so therefore I felt compelled to create this video in hopes that it will provide some useful information for you to get started at the very least. OrCAD is a very powerful, probably the best electronic design automation software for creating schematics, doing PCB work professionally. It's very expensive, so obviously if you're an individual person, you may not have access to it, unless of course you're a student or have very, very, very deep pockets. And because it's professional, it has many features that, but at the same time, there's a lot to learn, and it's not very easy to get started on using this software. So part of my motivation to creating this video is to provide you some information that will be useful for you to get started, and to go from I was intimidated by using this, but now I'm familiar on using the software, I'm comfortable using it, and I hope that it will be sufficient information and it will give you enough confidence for you to figure out the rest. You will probably have more questions after you're done watching this video, but I hope that you have enough information and enough of your own drive to kind of figure out things on your own, and use Google and look at other Google YouTube videos on, for example, on OrCAD to use very specific features of the software. So if you are here and you expected only a tutorial to show me how to use the software and be done with it, this is not what this video is about. This video is about using it will be presented in a lecture format. So I'm going to show you how to use the software, but I also need to provide additional information about about the whole process of PCB manufacturing that is important, that you just cannot capture in just using just the software. So I want some of the information to be generalizable, not just to OrCAD, but also to when you use any kind of the electronic design automation tool, EDA tools, for doing this. Just note that I will probably make a lot of mistakes. Sometimes I will say things that I'm saying certain things, yet I'm showing you something completely different. I was a little bit nervous making this video and being conscientious of the time. I made a few mistakes along the way, so I hope that you can pick those up. And I say this because I'm actually recording this introduction last. I've already created the tutorial videos, and I'm now just finishing up with the introduction, which comes first from your perspective. But please forgive me for those mistakes, and I hope that you are able to kind of just figure out the rest, and that overall the information that you get, it will still come across and it will still be useful for you. Lastly, before I get started, I do mention University of Nebraska. Again, I'm a teaching assistant and I work for them, but I'm also a student. When I use their name, that does not indicate in any way that they I don't know what's the right way of saying it, but that they're sponsoring what I'm necessarily doing, or that there's necessarily approval or any of that. It's implied. And also that my views and my opinions in this video and the other videos, and I will make views and opinions, are strictly my own, and they're not the views or opinions of the faculty and staff of the University of Nebraska. This is something that I'm just doing on my own, and hope that it will help other students when they're learning how to do this, because it's not an easy thing to do. So, having said that, let's just go ahead and get started. So I'm going to start with an introduction first, just give you some general information before we actually start looking at the software, and we'll proceed from there. Okay, so the topic is, again, Introduction to OrCAD Capture for students, but let's talk about the process itself at 30,000 feet. So when you want to learn how to do a PCB project, obviously you need to learn how to use what's called collectively called the Electronic Design Automation Tools, or Suite, EDA. So EDA software, I'm gonna be using that term. So when you're trying to learn any EDA software, there's always two stages. Okay, and I'm not saying this from the context of a design in a corporation, just simply on using the software. You want to know how to draw the schematic, and let me just kind of see if I can help you visualize it. Here, we have two phases. Okay. And the first phase is basically that we want to do how to draw the schematic. Okay? And then the second phase, of course, is that we're going to take the schematic and we're going to do the PCB layout and routing. Right? So these are the two major phases at 30,000 feet. Now, okay, to do this in terms of the software, there are at least 4 tasks that you want to know how to do. And again, the question is, how do I draw the schematic? What does the schematic software looks like? And for that, we're going to use OrCAD Capture again, which is shown here. So this is what a finished schematic looks like on your design. All right, you have symbols, you have lines connecting wires, electrical connections representing electrical connections from point A to point B, and nodes in your design. You have schematic parts, etc., etc. This is a schematic, and for the answer to this question for us is OrCAD Capture. Okay. Then the other thing that you want to do when you're doing the schematic is that you may be required to create your own components, right? Schematic programs, usually they have a good, rich library of symbols that you can use, but there are often times where you just need to create your own symbols, and in order for you to do this, you need to learn how to create symbols. So the other question that you want to have is, how do I create custom symbols? Okay, or components, right? So these are tightly integrated, right? You wanna know when you're drawing a schematic, obviously you may be called to create custom symbols. After you are done with this stage, the result of this is that you produce a file, usually called a net list, which basically is a file that encapsulates all the electrical connections of your circuit. All right, and that is imported into another component of the software, which is usually separated. And this is how do I do PCB layout and routing. Okay, layout means that you just place the components and you lay them out spatially in two-dimensional space on the board where you think the parts are going to be. The routing consists of basically you laying out the traces or drawing the traces in accordance to the net list that you generated from your schematic. Okay, so that is, we're going to do that, and we're going to explore this in a separate video. We're going to look at PCB Designer, and this is essentially what a finished layout looks like in PCB Design. Okay, so your schematic symbols basically are manifested on your PCB board as form of footprints or components that have a physical attributes and pins and shapes that you have to map to from your schematic design. And again, we're going to look at that. So that brings the other question is, how do we create custom footprints if we need to create custom footprints? Okay, because again, when you're doing a PCB layout, it may be the case that a symbol on your schematic capture already comes equipped with a footprint, or it comes with a library of footprints that you can apply to common components, for common package types that you can apply to your schematic components. But a lot of times you may have to create your own custom footprints, and for that you need to know how to do that. And this is usually part of the PCB layout, or it may be necessary to do in a separate package. In OrCAD, however, there's also a separate. Let me show you before I do that. What I mean by footprint. So you have a variety of packages here. You know, each package can have a footprint that you may need to create for it. For example, here is a figure of a board with some parts just placed on it, and we have basically the footprints for a variety of parts. Some of the parts are called through-hole components. That means that the pin, when the part sits on the board, will go through the board itself. So there are holes that are drilled that are part of the board, and these are usually plated through holes, right? The pin goes on one side and it comes out on the other. So you have this is called a footprint. Collectively, the package itself in the PCB board is called a footprint. So there's a variety of footprints. Notice that each footprint is composed of a series of pads. Okay, so this one has 8 pads, and so depending on the package type, this is a through-hole component. You have through holes, pins and pads. Okay, some packages are surface mount. That means that they only sit on one side of the board, and therefore you don't need through-hole pads, but you need pads nonetheless, where the parts is going to sit on when it's soldered onto the board. Okay, so these are footprints, but the footprint itself is composed of any number of pads. And for this particular part I'm highlighting right here, all of these squares are pads that are part of the component. So we have a footprint, and the footprint is composed of one or more pads. In OrCAD, pads, some programs allow the footprint creation and the pad creation to be part of one program, but in OrCAD this is actually done on a separate program called Pad Stack Designer. Okay, that means that before you can create footprints, you have to have designed your own pad stacks, pads files that you will be using. Then you use these pad files to then create the footprint itself using these pads, and then you can lay the footprint. Once you have created it, you can use that footprint many times onto your PCB board, and you attach that footprint to components in your schematic software that make use of that. The last stage after we're done with the PCB layout is that we produce a series of the end result of this endeavor, which is very complicated and very lengthy. The end result is we produce a series of artwork files. okay, which the de facto standard is files that are called Gerber format files. Okay, and let me just show you here for our finished project. Okay, I'm using a program called ViewMate from Pentalogix, which is a Gerber Viewer. It allows me, once I have generated the Gerber files from OrCAD, once I am done with this, I produce Gerber files. Then the files, I can go ahead and import them into a Gerber Viewer, and in my case, ViewMate, and then I can view the individual files on top of each other, and the result of all these files is that it represents your entire board, right? So we have, let me just go ahead and turn them all off so that you can see how the board builds up in layers. So we have an outline, and a Gerber file is basically a vector-based drawing image file. That's really all it is. I mean, it is more than that in a technical context. We're just simplistically looking at it. It is nothing but an artwork. That's what it's called, an artwork file. There's another reason why it's called artwork file. It has to do with historical reasons, but to keep things simple, it's just a drawing, right? So we have one layer that just tells the manufacturer how the board should be cut. And you know, many boards are typically square, rectangular in nature, but you can have any shape that you want. Then let's look at the top. So we're going to look at a top layer and bottom, two-layer design, right? So on the top layer, I have a copper layer, okay, that shows all the copper features. So I have the pads where the chips are going to sit on. I have pads where the connectors are going to be. Notice that this layer only contains copper features. All right, it doesn't matter what it is, what it is connected to. The file doesn't care. It doesn't know what's a chip or what's a part or what's a component. It's just copper features to the layer. Notice that there are no holes, right? Because this layer only shows the copper features. Because the drilling of the holes, if that is necessary, comes at a later stage. Okay, on top of that, of the copper, we usually protect it with another layer called a solder mask. And to show you what it is or its function, I'm going to reverse this into a negative and really see that what the solder mask does is that it is a thin layer of plastic or material that covers and protects your board and the traces of your board, and is only exposed at the points where we're going to make electrical connectivity with the components. Okay, but the rest is just covered up. All right. And that hurts my eyes, so I'm going to put it back onto positive. Okay, and then after the solder mask, we have the silk screen, which basically is a legend. It's usually in white, and I show you that over here in this image. Basically, all of this is just painting that is applied last on top of your solder mask, which is usually green. And it just gives you information of where the parts are, what the reference designators are, etc., etc. And then the same thing for the bottom layers. And then we have the complete board, and you usually have some text like revision number. I have my revision numbers on the bottom side, and that's why it's looking reversed. I have my name or a name, and a you can designate your institution. In addition, notice that again I have no holes in here. It's just copper features and pads. After the design is produced, then the manufacturer needs to drill holes wherever holes are needed. And to do that, we have a separate file called an NC drill file. And that is, it shows you how the holes then are drilled. So all of the parts, we have pads surrounding the hole. In this image, it's shown in white, so it is drilled through the board itself. Then we have the copper pad around it that is connected to the trace, and then we have some clearance between the pad and the solder mask that protects your board. And again, let me go ahead and reverse that to make that point clear. All right, so the solder mask protects everything else except where we actually need to have contact with the actual copper. All right, so there it is for you, all of these stages of and then for artwork, there's usually two predominant formats. One, the Gerber files. The format of the Gerber files is actually RS274D, which is an old school and older version of the Gerber files. And usually if you use RS-474D to produce your artwork, you usually have to also provide a separate file called an aperture list. And we will talk about what all this means later when we look at the PCB layout stage. We're not going to do this in this video. And then in addition to that, you have to provide the separate NC drill file. So the NC drill tells the manufacturer where to drill the holes. Okay. The modern version of this is actually the standard today is basically RS-274X. And basically this file it takes the aperture list and is embedded into this file. So you only provide one set of files and you don't need a separate aperture list. So you would provide a manufacturer just with your artwork files for just all your layers, and then a separate NC drill file. And your manufacturer proceeds from this, okay, to produce your actual PCB board. And that's what you get in the mail once you wait for it for approximately 2 weeks. Okay, so that is the process at 30,000 feet. For any, it doesn't matter. This is not an OrCAD thing. This is just in general what you need to be aware of. And again, we're going to look at these details closer detail as we progress through the tutorial in this one, and then on the PCB layout stage. So I suspect that there will be 2 major videos, one for the schematic side and another video for the PCB layout. It may separate, depending on the length, may separate the individual videos into sub videos. And then I hope I can get my aim is to look at the schematic and the PCB layout and show you how to generate the Gerbers. But I hope I can also do videos for generating or creating custom symbols for using your schematic, and how to create custom symbols for use in your footprints. Okay, so for the tutorial, again, we're going to use OrCAD. We're going to start with OrCAD Capture. We're going to get to all of this later. We're going to start here. Let me show you where we're going. Oops, OrCAD Capture. This is what we're going to design. We're going to look at in our video. We're going to create a 3-bit register. We're going to create what is called a hierarchical design within OrCAD Capture. All right. Again, demo version. This is 16.6. You can download this for free from Cadence once you register with them. Let's see what else. So note that in our notes for my students that we have 16.2, I believe. So you need to be careful because these versions are not necessarily compatible. So work as much as you can with just stick to one version. But the videos will all be based on the demo version. So there may be features that you see that I use that may not be available. So again, I trust that you will have enough knowledge to figure the rest out when you find these inconsistencies with the software versions. So we have here what we're aiming for is basically, and we're going to start this from scratch, but what we're aiming for is for a 3-bit design, hierarchical design. The reason why this is called a hierarchical design is because I am making use of what are called hierarchical blocks, which is a very nice feature for making or keeping your designs clean, and they make sense from a hierarchical design standpoint. If I take this block right here and I descend onto it by double clicking on it, I can see the structure and the implementation of that particular block. And this is essentially a latch, I believe. We have a data input line, and it's this 1-bit data input and data output and inverted output Q and Q naught, and then it's clocked, right? What I did with this design is that once I created this hierarchical block, I copied and pasted it 2 additional times, and each one, once we do that, we create what are called occurrences. But there are certain things that we need to make sure of, is that we need to make sure that, and I will show you how to do this, is that the reference designators are unique among the occurrences. If this is not the case, then we have problems. So I'm going to show you how to do this design. Again, the point is not how to be an expert. I just want you to learn how to do the basic things. We're going to use connectors, simple connectors for connecting the data input and retrieving the output. We have buses. We have net labels that we apply to the buses. We have some additional text that I've added for clarity. All right. We have another title that I've added here on the schematic. We have title blocks. All of the designs, they have title blocks. Traditionally, are we going to show how to do? And this is where we're headed. So let me just give you a quick tour. So this is the design area, and this is of course where you do the majority of the work. So you're going to be placing components onto your schematic sheet, and then after that you're going to connect everything together by placing wires and buses. On the right we have the draw toolbar. All right, and as you can do most of the work from here. So as you're adding parts, you click the add component or place part icon. As to connect wires, you use the connect wire. If you want to put a ground, there's the ground symbol. If you want to put a power symbol, there's a power symbol right here. If you want to place a no connect, you can place it right there. One thing I like about OrCAD Capture is that it's very simple. It's very intuitive, actually. It is the part when we get to the stage where we start to make decisions that are related to the PCB board itself, where complications begin to arise. But the drawing of the schematic is so simple. You just place components, and then everything's intuitive. The keyboard P is for placing components, W is for adding wires, B is for drawing buses, E is for drawing bus entries, N is for drawing net aliases or net labels and applying them. F is for power, G is for ground, R is for rotate when you're rotating the part. Everything is very simple, very intuitive in OrCAD Capture. So the problem really is in OrCAD Capture. The challenge really begins when we move on to the PCB editor, PCB Designer, and because it's just the paradigm of using Capture is so different from what you may be accustomed to in regards to expectations of how you feel a program should behave. Your interaction, mouse buttons and mouse movements and keyboard shortcuts, etc., the way it works is just different, and this is the part where it can be frustrating. And again, the reason for me creating these videos hopefully is to alleviate some of this frustration. So we have design area, toolbars. The third window that is very important is the project window. Okay, as you create a variety of files in your design, some of these will already be placed in here, but what is important for us is basically our design here. Every project has one or more designs, which is indicated by your .dsn file. Okay, the project itself is saved under .opj file name, but inside of that project can be associated with multiple designs. In our case, we only have one design, which is our simple design project, which we're going to do. Each design can have one or more schematics. So therefore, my design consists of two schematics, which I have purposely renamed to top for the top level schematic, which is this my top level hierarchy. And then I have another page design, a schematic, not page, schematic, called flip-flop subsystem, which is basically the stuff that is inside of here. So this is a flip-flop subsystem. But notice on my project manager, I only have one schematic, yet I have three different occurrences, right? So I only have one schematic to represent the implementation of my hierarchical block, but then I have three separate occurrences. But the project manager only chose the one sort of template from which the occurrences are derived from. Next, each schematic can have one or more pages. This is very important. Let me illustrate what it is meant by pages in OrCAD. Let's go back to let's do a new window here. Okay, in OrCAD, schematic can consist of a large sheet of paper. Okay, this could be a very large sheet, not just 8.5, right? And maybe this sheet is of a particular subsystem. Okay, maybe this is a schematic for your power supply. Maybe your power supply is too big. Maybe you're using 8.5 by 11 sheets. All right. So your schematic, let me make sure that this is the schematic, right, can be divided into one or more pages. And I'm showing it this way to illustrate the principle. You can divide however you want, right? So therefore, this schematic has a page 1, page 2, page 3, and page 4. And maybe in this page you can have the control electronic component of the power supply. Maybe in this page you can have the analog components of that are low voltage of the power supply. Maybe in this page you can have the high voltage components of the power supply. So we have a schematic indicated by a folder in the project manager, which consists of 4 pages that stand side by side. The way that you connect a component or a wire from this schematic to another page is that you use what are called off-page connectors, which is indicated by this symbol right there. And this connects to another off-page connector on another sheet. And the off-page connectors are specifically for this purpose. So, going back to Capture, my top level has actually only needs 1 page. I added this additional page to show you. And then my flip-flop subsystem only has that 1 page. And when I double click on it, it asks me which occurrence I want to select because I copy pasted it 3 times, right? So you click on it and then you're taking that occurrence. I actually only need 1 page, but I wanted to show you, and I probably accidentally saved this and I didn't intend to. So you can remove the sheet that you don't want, but it will say that it cannot be undone. You say OK. If you want to add a schematic sheet, basically you select your schematic and you right click and you select new page, and you could rename it or you could leave it as is. A new page is added, you can double click on it and you can start adding parts on it. Okay, so that's how you do it. But if you don't need it, you can just right click and then you can remove the if you cannot delete an open page, you just got to make sure that you select the page, you close it, right click, close it, say yes, no, I don't want to save the changes, and then after that the page goes away. Now there's one last thing I want you to notice is that the project manager schematics has /. This means that the schematic with the // is the root page, and this is necessary for hierarchical design. When you have a hierarchy, you have sort of like a pyramid. Well, what is the top design that connects all your blocks? Well, you can designate a schematic as your top block by simply right-clicking and selecting Make Root. But because this one is already the root, it is showing ghosted. But if I wanted to make my flip-flop subsystem as root, which doesn't make any sense in my case, I would just select Make Root. So that's how you do it, and that's our basically an introduction to using the Capture. Just a quick tour. If you don't see the notice that there's certain things that happens when I have a schematic selected, the draw toolbar gets ghosted. I can't do anything. If I double click on a page and move over here, then the toolbar becomes enabled. There are certain things that you can do when a page is selected versus when a schematic is selected versus when your entire design is selected. Particularly right up here, we're going to be using these. We're going to re-annotate our design when we're done. We're going to do a design through check, and then we're going to generate the net list. And these are things that are drawn globally for the whole design. So you have to make sure that you have the design selected. The star indicates that we need to save. So usually Control Save will take care of that and save the whole design. I also want to make you aware of a few other things. So if the draw toolbars are not visible or you lose them for whatever reason, just go on to Tools, View, Toolbar, Draw, and that's how it shows and goes away. Okay, so that's how you find it. Another major window I want you to be aware of is the session log. Session log is not visible right now because I want as much space as possible, but the session log, which you can access by going to Window, Session Log, is basically an output window that shows you any information. Whenever you run a command, the results of these commands will be displayed on the session log. So you need to go in here, say when we do a DRC, Designs Rules Check, and we want to see if there's any errors, you need to look at the output of the session log in the session log to see if there were any errors or not. So again, I'm going to dismiss it, but again, Window, session log. Okay, now before I actually start with the tutorial proper, I want to show you basically some examples of good design versus what's not good design practice, because sometimes what is obvious to some of us who do this is not obvious for the beginning. All right, and this entails basically the question of clarity. Your schematic has to be clear, not just to you but to other people who will be looking at design. Same as when you write code. You comment it not just for yourself, even though you know how the program works. Other people may work on your software and they need to know what you were thinking, or they need to be clear on understanding how the program works. So clarity is very important. So let me just show you some examples of schematics that you should look at for inspiration for doing your own work. Okay, so let's take a look. Good schematic, bad schematics. Let's see. Some schematics here. Let's start with some bad schematics. Let's see. Here we have a schematic that I used in the past for. We used the CMU CAM from SparkFun, and CMU Carnegie Mellon University, and they have. This is a schematic that was offered. For the board, and it shows you one of the biggest problems that I have with many of what are so-called open hardware schematics that I see put out there, probably because of inexperience, and that is, this is what I call basically a fragmented design. Okay, and basically what we have is nothing but a schematic pages with symbols just pasted on it. And I look at this and I just cannot really tell what is the general flow of the signals in the design, and I cannot really see immediately what is connected to what. What we have is incomplete parts that are placed with just basically pins, the pins around it, and basically a net label, and I have to basically navigate and search the entire design to find how many occurrences of the label camera D2 occur in the schematic. Of course, this being electronic, I can try to do a search and find it. But if I have a printed version and I have to myself pick up a pencil and I got to draw lines, so this is not very clear, and this is something that I highly advise students and professionals alike who are doing this not to do this. I know that this makes sense to the person who's drawing the schematic because you drew it and you know where everything is, but when another person is looking at it, they have to search through this use schematic and waste time because this is not clear. Another motivation I believe this comes from is from basically trying to pack the entire design into one single page, as if pages was a scarce resource, especially when you're going to have an electronic supply the design as in the form of a PDF. Okay, you have pages, spread it out, put the power supply subsystem in one page, put the digital subsystem in another, put the connectors in another if you need to, or try to connect as much as possible so that my eyes can see where everything goes, instead of my eyes having to just search for where everything is. This is not clear documentation, and you should not follow, you should avoid this practice. Here's another example from a product called the SceneBot that we use, and this is from a fellow that have hold in very high regard. Worked on this product, and I've also did a lot of programming for the SceneBot, and this is one of the pages as an example where everything is in here, but again it's just a page consistent of a fragmented design, right? I have a chip with pins around it, and they go everywhere. Where do they go? I don't know. So I have to search for the information, and then everything, all the different domains of the circuit are all in one page. I have connectors in the same page. I have power supply subsystem in the same page. I have the serial port in the same page, regulation in the same page, the display connection in the same place. So I have to search for everything, and what I ended up doing, and I printed this out. Well, I didn't print this out. I actually took a blank sheet of paper and I redrew the power subsystem from scratch, and then I just drew the line so that I could always find my way when I needed to find that information. So again, this is something that to the designer it makes perfect sense. The person can always find the information they need, but when others are looking at your design, it's not something you want to do. So what's an example of a good design? Well, SparkFront has a few also. I just look at some of their open hardware platforms, and they are highly they seem to be very they use Eagle as their preferred software. So this is a cleaner design, although we kind of have the same problem. This is cleaner, not crowded. There's some things like, for example, the text here, it just kind of goes out of the border. We have some of the things are clear, but again, we have that situation where we have a pen going to a bunch of terminal lines, and you have to kind of search for them. But because this is simple, this is easy to kind of figure out. But that's not much of a big deal there. Let's look at a photo board. This is a really nice design here. This is very clean as far as cleanliness goes, and they have been very clear about the subsystems and what each part or region means in the schematic. So we have the supply subsystem, we have the USB part where power is obtained. Also, we got the microcontroller, LED. So all of the major subsystems are clearly delineated, but again, there seems to be a lot of effort on making sure that all of this fitted in one single page. I don't know why. Again, you can use bigger pages if also, which is a thing that I like to do, or you could have used additional pages. But again, we have the same problem where terminals we have a part with terminals, and we just don't know where everything goes. Now, a lot of SparkFront parts are just development boards with the parts on them, and then they just go onto the connectors and nothing else. So in such cases, it's usually okay. For bigger designs, something that you want to avoid. Here in XP Explorer, again, very simple, very clean. But I would have preferred, what is this? What does this region constitutes? Information for me to know about. That would have been nice. Another complaint that I have, and I think this is probably because of Eagle, is their use of the ground symbol here. Okay. I don't know why, but many EDA tools actually use that as a supply pin and not as a ground pin. Excuse me. The symbology for electronic system has been clearly defined by the IEEE standard. I believe is 375, 1997. 315, sorry, 315, 1997, or 1975. So the ground is very well defined. There's no ambiguity. We only have three principal ground symbols that are used in a lot of the literature of electronic circuits, and that is the earth ground, chassis ground, and the digital ground. So usually this is the analog ground, this is the chassis ground, and this is the digital ground in electronic systems. And so the addition of yet another symbol custom made for it to mean ground, it seems kind of silly to me, and it leads to confusion because a lot of the professional EDA tools actually use the same symbol upright to mean the positive side of a power source, which is BCC, which is the same as this, which is the same as, sometimes you have the arrow pointing this way. So I really don't like this. I don't like this practice. I think I don't know if this is because of Eagle. So I don't know if I should be saying thanks Eagle, but you should stick to the standards. Okay, when you use grounds, use proper grounds. If you use the proper grounds, you actually don't have to label it ground. It is understood that the ground is ground, and if you're working in Eagle, you see this, and then you move on to Cadence or some other package. For example, Ultimed Designer also uses it. You'll be confused. So that's a personal opinion, again, but I just want to make you aware of that. There is a standard that says what our ground symbols are, and this is not a standard ground symbol. So you should avoid that in your designs. Oh, one more thing. I almost forgot. So I showed you bad design. I show you so-so design. What a good design should look like. I have some examples, some of the designs I have done that I've also seen professional companies do, like for example Texas Instruments or Analog Semiconductor. You should look at the way that corporations do schematic designs, because they do very clean professional designs. But for example, for my senior project, we did something that had to do with audio, base station. Let's see if this is shows me. So this is entire design. It's a hierarchical design also, and I made use of hierarchical blocks. This was, for the record, this was done on Altium Designer in a entirely different EDA suite. But you can also do this in OrCAD. Okay, so this is also a hierarchical design, and we have hierarchical blocks. And the way that hierarchical blocks are connected together is by way of hierarchical ports. Right? And basically what I did is I separated my entire design into subsystems. And so I have the MCU subsystem, then I have the sound subsystem, and then the display subsystem, wireless subsystem, and the physical interface subsystem. And then after that, each subsystem was sort of the sound block subsystem has further areas of certain further blocks beneath it, input stage, the conversion stage, the ADC stage, etc., etc. I also drew my own symbols. Again, an example of why having your own symbols is useful, where I could use jumpers that are variety standard symbols that I use, but I wanted to be clear that these are the standard jumpers that you see in many development boards, and so I drew my own symbol to do that. So this is an example where knowing how to do your own component symbols in schematic capture can be useful. Okay, but this is a clean design. Notice that the signals, they usually flow from the left and they move on to the right, and this is a practice. You know, power is like water. And similar to gravity, it starts from the top and it just flows downwards towards the ground. And so power should be from top to bottom, and then signal flow should be from left to right, kind of like rolling down a hill. Okay, here's an example of a sheet for the power subsystem, and again, I was not afraid to waste an entire sheet. All of the information about the power subsystem is just in this one sheet. This is the microcontroller subsystem, and again, I kept it as clean as I could, consistent as I could, delineated separate parts away from another so that there's no confusion. Connectors, I kind of drew my own connectors because I knew these were going to be upright, etc. For clarity, again, use my own jumper. I kind of designed my own coin battery symbol so that it was clear it was a coin battery instead of an arbitrary symbol. Again, display subsystem is in its own page. I drew the display diagram to make it clear how the flat flex cable connects to the connector, to make everything as clear as possible how the power cable connects, and keep that clear. Here's the wireless subsystem again, because that's all it took. Everything is on its own page. Pins that are not used are designated as no connects, and then we have the interface coming from the right, etc., etc. We have the volume subsystem. Again, I use symmetry for clarity. Everything's kept together. Signals come from one side and they go out the other. So everything's very clear. Notice that this is not a fragmented design. It is fragmented in the context of subsystems and hierarchies, but the circuit is completely all wired up. So I can follow the eye and see where the lines are connected to other lines. If I just drop symbols and just use net labels everywhere, this would be a nightmare to understand, but also to debug. You waste time if you're debugging a circuit because you keep constantly having to search for information that is not there. Again, analog block, so signals coming from the left and the output on the right, and the use of symmetry and clarity. And for the bypass capacitors, again, down here, delineated into its own box so that it doesn't interfere with the rest of the schematic symbols. So this is an example of good design that I hope that you are inspired to follow, to keep your design clean, to keep your designs looking really professional. It provides an impact to those evaluating your work. This was for my computer design class, not computer design, embedded systems design class that I took when I was an undergraduate student. See, if I don't know if I have everything in one page here. So I have a cover page where this was back in 2011. I always provide a cover page. I put a sheet that I use for a cover page, and then I just add big text on it so that when I print it out, I can put that in the front of the cover of the sheet. Then again, top level design. Right, I use hierarchical blocks for complex designs. It's very, very useful. It's a good strategy. MCU subsystem, decoding subsystem, USB subsystem, the JTAG interface, and again, I can see where everything goes. I can follow the eye. It looks a little bit like spaghetti sometimes, but you can follow the eye, and it's easy for when you're debugging your design. let's see, core MCU again. I use a similar style that I use in the other design that I show you. So everything's connected. Everything that's related to the subsystem is connected. There's nothing. There are no fragments of symbols just left on their own, except for where it's obvious in common practice for bypass capacitors, for example, to be left on their own. But everything else is connected within the subsystem. So you spread everything out for the purpose of clarity, but you keep everything together within the subsystem. Everything's connected together to make it clear and debug and understand the subsystem all by itself. This is good practice. Again, personal opinion here, but I highly recommend that you should follow this professional practice and aim for clean, clear, professional schematic designs when you draw your designs. It's a habit that I recommend that you start up from the get-go. Okay, keep your designs clean. All right. Okay, so that's it for the introductory part. Now the next part that we're going to look at is basically we're going to work on this design. I'm going to show you how to do this design from scratch. So I'm going to go ahead and dismiss all these windows, and we're going to back to here. We're going to start with OrCAD Capture CIS. So again, what you're going to find out is that the schematic is a piece of cake. Actually, it's when we need to make decisions about the PCB itself where we start to have problems, because that requires a lot of research and that you find out a lot of information ahead of time. And then when we move on to the PCB editor, then that's when things get challenging, because there's a lot of information we have to digest for us to successfully do this. One thing I want to point out before I finish and start on that is take a look at there is a book, because there's so much information, and OrCAD or Cadence doesn't necessarily make it easy for you to find that information, is to look at a book called Complete PCB Design using OrCAD Capture and PCB Editor. A lot of my questions when I was getting started with OrCAD were answered and obtained from this book. This is a really good book, not just about PCB design using OrCAD, but it shows you also about the theory and some of the important information you should know beyond just using the software on doing PCB design. Okay, so you should have this in your shelf if you do PCB design extensively. And that's it.